All right, in this video, what I want to do is I want to talk a little bit more about countable and uncountable sets. So we've seen before, I think it's worth just now writing everything so that it's all in one place. A set is finite. So a set is finite if it contains finitely many elements. So again, nothing new there, nothing terribly interesting, dare I say. So if it contains finitely many elements. A set is countable. So a set is called a countable set. And in fact, maybe it'll give a little help if we call this set E. So set E is countable if there exists a bijection. So if there exists a bijection from E to the, say, non-negative integers, or from the non-negative integers to E, because we know that if F is an inverse, if F is a bijection, then its inverse is a bijection. So the order doesn't matter. And also we know that the composition of bijections is a bijection, meaning that we can replace the non-negative integers with your favorite countable set. So the positive integers, so maybe you don't want to include 0, maybe the integers themselves, whatever. So a set's countable if there exists a bijection from it to the, say, the non-negative integers. And then one last definition. So a set E is going to be called uncountable. So set E is uncountable if there exists a bijection from E to the set of real numbers between 0 and 1. Doesn't really matter whether you include the endpoints or not. So that's what it means to be uncountable. So now we have three types of sets. We have finite sets, and then infinity comes in two flavors. We have countable and uncountable. And countable, again, is we're going to see is much smaller than uncountable. So when we had an uncountable set, it didn't matter how carefully we constructed it. A bijection, we're always going to miss something. There's always more stuff in the uncountable set than there is in the countable set. And again, another way to think about countable versus uncountable is that countable, I like the word listable. So here countable really means that you can write everything down in a nice ordered list. So that's what countable means. Uncountable really means unlistable. There's no way that you can write down all the elements in the interval from 0 to 1 in a nice list. So I kind of think of listable as a synonym for countable, even though that's not really an official math word. But that kind of helps me kind of map what's going on. So that's finite, countable, and uncountable. And then we've already seen that the integers, the even integers, even the rational numbers are countable. And all we've seen so far is just one example of a set that's uncountable, but it turns out that there's lots. So the interval from 0 to 1, really any interval from A to B, as long as A is less than B, as long as, of course, it's not a empty interval. So any interval from A to B is uncountable. And again, it doesn't matter whether you include endpoints or not, or even half endpoints or not. These are uncountable. This includes, by the way, R. So the real numbers themselves, okay, are uncountable. Okay, and there's a few propositions that I want to walk through. The first, so I just want to do this kind of very carefully. The first is that so I'll call this a proposition. And again, this just, I think, makes, this proposition will really make it useful to determine how to think about these. So finite sets are small, countable sets are big, uncountable sets are really, really big. And so here's how I want to write this proposition. Suppose that you have two sets, A and B, where A is a subset of B. Then the following is true. If B is finite, let me write this in a nice numbered list here. Okay, but if B is finite, then A is finite. There's no real mystery there, right? If A is a subset of B, that means that everything in A is also in B. And if B is finite, then A has to be finite, right? If B is small and A is a subset of it, then A is also small. If B is countable, then A is either finite or countable. By the way, whenever I say countable, I always assume that we're talking about an infinite set. Some authors and some books like to call countable sets, they like to include finite sets in there for whatever reason. But for us, whenever we talk about a countable set, we're talking about something, just notice how I've defined it. A countable set is one where there's a bijection to the non-negative integers. So inherently it has to have infinitely many elements. So when we talk about countable sets, they're infinite sets. So if B is countable, then A is either finite or countable. And if B is uncountable, then, and I'm not going to write this because it's a useless statement, but it's true. If B is uncountable, then A is finite, countable, or uncountable. It just doesn't tell you any information. On the other hand, if A is finite, that again doesn't tell you anything. B could be finite, countable, or uncountable. But if A is uncountable, then B is uncountable. And finally, if A is countable, so if A is countable, then B is either countable or uncountable. B has to be infinite, right? If A is infinite and A is a subset of B, then B has at least that much stuff in it. It has to be infinite, so therefore it's either countable or uncountable. And again, I just want you to kind of get used to the idea of small. Finite sets are small, countable sets are big, uncountable sets are really, really, really big. So that I think is a useful proposition for keeping in order the idea of finite, countable, and uncountable. That'll be useful for us. And from this, we actually get already a few things. We get, just going back, we get that the reals are uncountable because the reals have the interval from 0 to 1 as a uncountable subset. So here we could take A to be the interval from 0 to 1, B to be the reals, and then apply, I guess it's item number 3, the way I've written it. So yeah, so the real numbers are uncountable. Another proposition that is useful is that if A and B are countable sets, then A union B and A cross B, the Cartesian product of A and B, are also countable. Okay. And the proof is straightforward. So the proof for the, say, the union, let's say A and B are countable sets, meaning that you can just write them in order and start at 0 if you want to start at 0. But you can write A1, A2, A3 all the way down. In other words, there's a way to list them. And likewise, B, you could write as B1, B2, B3. So this is really a sketch. We can assume, so you may assume for the sake of a union that these are disjoint sets, because if they're not disjoint sets, then their union is even bigger. So you may as well just say they have nothing in common. And then A union B is going to be the set A1, B1, A2, B2. And that's a way that you could systematically list off all the values in the union, and you can get a bijection that way. And again, if A and B are not disjoint sets, if they have some element in common, then just skip over it whenever you're listing out the union. That's fine. So you might as well assume that they have nothing in common. So there's the union. So that's, again, I shouldn't call this a proof. This is really just a sketch. Okay. And likewise, A cross B is going to involve some arguments that we've seen already. A cross B, the Cartesian product, is going to be, you can write it as follows. You can write it as A1, B1, A2, B2, A3, I'm sorry, A2, need to be more systematic here. A2, B1, so I'm going to make B1 the second component in the first row. So A3, B1, A4, B1, and so on. And then in the next row, you have A2, A1, B2, A2, B2, A3, B2, and so on. And then I'll just do 2 more rows. So A1, B3, I don't know why I keep confusing these. A1, B3, A2, B3, A3, B3, and so on. A1, B4, A2, B4, okay, and so on. And so you can list the Cartesian product in this way. Okay, so you can imagine that those are 2 big sets. And then how do you want to count the elements? Well, you could count along diagonals again. So you could count, say, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. And then you can see that you'll eventually hit every value there, or you can be a little bit more creative and zigzag, which is my preferred method here. All right, so you could zigzag that way. And again, you'll hit every element, every pair in the Cartesian product at least once. And those are proofs enough. So again, those are sketches kind of in the same vein as when we proved that some concrete sets were countable or uncountable, like the even positive integers and so on. So really, if you can just list them all out, then we're good.